Welcome to this comprehensive lesson on pressure and flow measurements. Understanding these concepts is fundamental in engineering, industrial automation, and fluid mechanics. Pressure measurement plays a crucial role in ensuring safety, efficiency, and accuracy in processes involving liquids and gases. Likewise, flow measurement determines the quantity of fluid moving through a system, helping in process control and optimization. From chemical plants to power generation and even medical applications like ventilators. Pressure and flow measurement impact various fields. By the end of this lesson, you will have a solid grasp of the principles, instruments, and applications used in these critical measurements. Pressure measurement is a fundamental concept in engineering and science, widely used in industries such as oil and gas, pharmaceuticals, aviation, and healthcare. It involves determining the force exerted by a fluid, liquid or gas, on a surface. Why is pressure measurement important? Industrial safety prevents overpressure conditions in boilers, pipelines, and reactors. Process control ensures accuracy in chemical reactions and material handling. Environmental monitoring used in weather stations to measure atmospheric pressure for climate studies. Medical applications, blood pressure monitors and ventilators rely on precise pressure measurements. Example applications. In aviation, pressure sensors help determine altitude and airspeed. In deep-sea diving, they are used to monitor oxygen tank pressure and environmental conditions. In space missions, spacecraft use pressure sensors to monitor cabin conditions for astronauts' safety. Understanding pressure measurement is crucial for ensuring efficiency, safety, and reliability across various industries. Pressure is the force exerted per unit area. It is given by the formula pressure, P, equals area, A, divided by force, F. This concept is widely applied in industries where fluid control is required. For example, in hydraulic systems, pressure is used to generate mechanical movement, such as in car braking systems. In weather forecasting, pressure variations help predict storms and other atmospheric changes. Even in everyday life, we encounter pressure concepts. For instance, when inflating tires or using a syringe, there are three primary types of pressure. 1. Gauge pressure, PG, measures pressure relative to atmospheric pressure. A tire pressure gauge reads gauge pressure, meaning it shows how much pressure is inside the tire compared to the outside air. 2. Atmospheric pressure, PATM. This is the pressure exerted by the air on Earth at sea level. Approximately 101.3 kilopascals or 14.7 psi. It affects everything from weather patterns to human respiration at high altitudes. 3. Absolute pressure, PAR. This is the total pressure, including atmospheric pressure. It is the sum of gauge pressure and atmospheric pressure and is essential in scientific research and vacuum system. Primary elements are the components that come into direct contact with the fluid whose pressure is being measured. These elements must be elastic to deform under pressure and return to their original shape. Different primary elements are used depending on the application. For instance, Bourdon tubes are used in pressure gauges, while strain gauges are preferred in structural load testing. The material choice, such as stainless steel, bronze, or special alloys, depends on the fluid's properties, including temperature, pressure, and corrosiveness. A Bourdon tube is a curved, hollow tube that straightens when pressure is applied. This movement is converted into a mechanical reading. Bourdon tubes are used in a variety of industries, including petrochemical plants, to monitor pressure in pipelines, manufacturing industries, to ensure proper hydraulic pressure in machines, aerospace engineering, used in cockpit instruments to measure altitude and cabin pressure. They are robust, reliable, and can measure pressures up to 29 bars, 2.900 kilopascals. Though they lose accuracy at very low pressures. Bellows consist of a flexible, accordion-like structure that expands and contracts with pressure changes. They are commonly used in applications requiring low-pressure measurement, such as HVAC systems, to control airflow based on pressure differences. Medical devices, such as ventilators and anesthesia machines. Vacuum pressure measurement, in semiconductor manufacturing. Bellows are typically made from brass, bronze, or stainless steel, with sealed or externally pressurized designs. Diaphragm sensors use a thin, flexible membrane that deflects under pressure. These sensors are widely used in food and pharmaceutical industries, where cleanliness and hygiene are essential. Water treatment plants, to monitor water pressure and ensure efficient filtration. Automotive industry, in fuel injection systems for precise pressure monitoring. Corrugated diaphragms can handle higher pressures than flat diaphragms, making them versatile across different industries. The capsule consists of two diaphragms that have been welded together on their circumferences and are almost exclusively corrugated. The capsule is constructed of bronze, monel, stainless steel or other alloys depending on the fluid application. Its advantage over the board and tube is that it can withstand much higher pressures. Up to 300 bars, 30.000 kilopascals. Capacitance capsules are a very popular primary element in pressure and differential pressure transmitters. Capacitance is the electrical property that permits an electrical circuit to store a charge. A capacitor is the electronic component that exhibits capacitance and consists of two conductive electrical plates separated by a non-conductive dielectric material. The amount of capacitance is dependent on the area of the plates and the distance between them. A capacitance capsule consists of the capsule that is filled with a dielectric material. The two parts of the capsule are the plates and are of fixed area. Therefore, the only variable is the distance between them. If a pressure is applied to one side of the capsule, the distance between the two plates is decreased, thereby increasing the capacitance, since the relationship between the distance between the plates is inversely proportional to the capacitance. The change in capacitance is measured by an electronic circuit and is proportional to the pressure applied. These are commonly used in high-pressure applications, such as aircraft cabin pressure monitoring, differential pressure transmitters in industrial automation. Capacitance capsules use changes in capacitance to measure pressure, which is useful in electronic pressure transducers. Piezoelectric sensors use crystals that generate an electric charge when subjected to pressure. These sensors are used in dynamic pressure measurements, such as detecting explosions or engine combustion. Common in ultrasonic devices for non-destructive testing. Found in medical ultrasound imaging. The ability to measure high-frequency pressure changes makes them invaluable in scientific and industrial applications. Strain gauges detect pressure by measuring changes in electrical resistance. Applications include bridge safety monitoring, detecting stress changes in structures. Robotics, for precise force feedback in robotic arms. Biomedical applications, measuring blood pressure in medical devices. Differential pressure, DP. Transmitters measure the difference between two pressure points. They are used in industrial processes to monitor flow, level, and filter performance. A DP transmitter consists of a pressure capsule, ensures high sensitivity by detecting minimal pressure differences. A body with a display and electronics module, converts pressure readings into an electrical signal. A manifold with isolation, bypass, and vent valves, enables safe operation and calibration. Real-world application. In oil refineries, DP transmitters help monitor fluid flow in pipelines, ensuring efficiency and detecting leaks early. In power plants, They measure steam flow and ensure turbine efficiency. A 3-valve manifold protects pressure transmitters by preventing over-ranging when bringing the device in or out of service. The 3 valves include high-pressure isolation valve, isolates high-pressure input. Low-pressure isolation valve, isolates low-pressure input. Equalizing valve, balances pressure across the transmitter before removing it from the system. Application example. In the chemical industry, 3-valve manifolds prevent sudden pressure surges when measuring corrosive or hazardous fluids. Proper installation is key to ensuring accurate pressure measurements. Important considerations include selecting the right material for high temperature or corrosive environments. Stainless steel or ceramic components should be used. Avoiding high vibration areas. Vibrations can distort readings. Instruments should be installed in vibration-free zones. Using pulsation dampers prevents rapid pressure fluctuations that may damage sensors. Steam installations requires siphons to prevent steam from reaching the measuring device. Case study. In power plants, incorrect installation of pressure transmitters has led to faulty steam flow measurements, affecting power output efficiency. Flow measurement is the process of determining the quantity of fluid, liquid or gas, moving through a system. It is a critical parameter in industries such as oil and gas, water treatment, pharmaceuticals, and food production. Why is flow measurement important? Process optimization ensures accurate fluid control in industrial operations, reducing waste and improving efficiency. Safety monitoring helps detect leaks in pipelines and prevents overflows in tanks. Energy management used in power plants to optimize fuel and steam usage, improving overall efficiency. Medical applications essential in devices like IV drips and ventilators to regulate the flow of fluids and gases. Example applications. In water treatment plants, flow meters regulate the amount of water being purified and distributed. In oil refineries, they ensure precise measurement of crude oil and refined fuel movement. In aviation, fuel flow meters optimize engine performance and efficiency. Flow measurement plays a key role in ensuring accurate, efficient, and safe operations in many sectors. Throughout this lesson, we will explore different methods of measuring flow, including differential pressure, velocity, and mass flow techniques. Flow measurement determines how much fluid moves through a system over time. This is essential in industries like water treatment plants, to regulate the amount of water being processed. Oil and gas pipelines, to prevent losses due to leaks and ensure operational efficiency. Medical field, ventilators measure airflow to ensure proper patient support. There are several flow measurement methods, including differential pressure-based meters, like orifice plates and Venturi tubes. Velocity-based meters, such as magnetic and ultrasonic flow meters. Mass flow meters, such as Coriolis meters, used in precise industrial applications. Differential pressure flow meters work by placing a restriction in a pipe, creating a pressure drop proportional to the flow rate. Common types include orifice plates, simple and widely used in industrial applications. Venturi tubes, used in high-accuracy applications such as fuel flow measurement in aircraft. Flow nozzles, ideal for high-velocity applications, such as steam turbines. Example, in gas pipelines, differential pressure meters detect blockages by measuring pressure variations. Bernoulli's theorem states that the total mechanical energy of a moving fluid remains constant. It includes pressure energy, due to fluid's force per unit area. Kinetic energy, related to the velocity of the moving fluid. Potential energy, dependent on the fluid's elevation. This principle is used in aircraft pitot tubes, to measure airspeed. Blood flow measurement in medical devices, helps detect cardiovascular conditions. Fluids can flow in two ways. Laminar flow, smooth, parallel layers with minimal mixing. Used in microfluidic devices and biomedical research. Turbulent flow, chaotic movement. Common in industrial pipelines. Example, in car engines. Turbulent fuel flow ensures better combustion and efficiency. Reynolds number, Re, helps classify flow. Re less than 2000. Laminar flow, stable. Ideal for precise chemical dosing. Re greater than 4000. Turbulent flow, common in industrial fluid transport. Application. Engineers use Reynolds number in designing water treatment systems to optimize pipe diameters and prevent clogging. When a restriction is introduced in a pipe, it causes a pressure difference. This principle is used in steam power plants to optimize turbine efficiency, oil refining to measure crude oil flow in distillation columns. Differential pressure flow meters are a cornerstone in industrial fluid management. By measuring the pressure difference caused by a restriction, we can accurately determine flow rates. This method applies to a variety of fluids, liquids, gases, and even steam. Let's explore the formulas and principles at play. The first formula, QV equals K times the square root of differential pressure, gives us the core relationship between flow rate and pressure difference. However, in real-world scenarios, variables such as pipe diameter, density, and area ratios come into play. That's where the detailed equation helps refine the accuracy. In industries like power generation, this principle is applied to optimize steam turbine efficiency. In chemical plants, it ensures precise dosing of reactants. By understanding this flow equation, we unlock a powerful tool for process optimization. Accurate pressure and flow measurement is crucial in industrial automation, safety monitoring, and process optimization. Understanding these principles helps engineers, scientists, and technicians improve efficiency and reliability. Final thoughts. Aerospace. Pressure sensors ensure safe aircraft operation. Energy sector. Flow meters optimize fuel consumption in power plants. Healthcare. Blood pressure and oxygen flow monitoring rely on these principles. With technological advancements, modern sensors offer better accuracy, real-time data monitoring, and remote control capabilities, ensuring efficiency in various fields. Next week, we will continue studying flow measurement,